All right, back from break. I did do a quick fix on this. And so what that said was the net electric field at point P is given by adding the electric fields at P from each of the two paths. That's interference, that's quantum mechanics. So again, this is just a drawing of what we've been working on. This is kind of interesting too. We've been calling this distance x, but somehow it turned into y. Everything else looks the same. Two slits, distance between the slits, angles are defined the same way. But x has turned into y. Why? So here is a technique where we can go in and we can analyze not just two slits, but 3 or 4. We could analyze different sorts of source patterns to predict what the interference effects will look like. And so what we could do with just the two slits we're working with now, there's 2 possible paths. Each path is considered to have the same amplitude. So each path we're imagining is contributing equally to the final overall interference pattern. Now the relative phase between them, I'm going to call that phi. I think that's the same notation our textbook uses. Anyway, remember this is just a relative phase. It depends on how much phase one path has with the other. We could just as easily have said this phase is 1/2 phi and this phase is minus 1/2 phi. We just need something that says that, going back to this picture, as we move along the screen, the difference in length of the two paths will steadily increase, and it's given as an approximation as d sine of theta. So that's the extra distance. Okay, that is being introduced along here. What that means is that when I look at different points along the screen, at this point the phase difference is 0. The two have exactly the same phase, and there's no phase difference present. If I move here, we're beginning to see a little bit of phase difference, a little bit of phase difference, a little more. Let's say this point is m equals 1. If this is m equals 1, then it says what we've got here is 1 exact wavelength. Now, what happened in getting from m equals 0, where the phase is matched right up, and m equals 1, that's the same thing as 1 complete cycle. So how would that be represented on the phase diagram? Well, on the phase diagram, what we would do is we can draw a coordinate system. We can take path 1, let's just have path 1 be right along the x-axis. Now, if the two paths are right in phase, then the phasor representing path 1 and the phasor representing path 2 would be lined up exactly. And that would say that the total amplitude would be A from path 1, and A from path 2 would give us 2A. We would have double the amplitude. That's going to give us a lot of intensity. But as we move along the screen, the phase difference is going to increase. Now the phase difference isn't the same thing as the angle. The phase difference comes from, as the angle increases, d sine theta increases. If I take d sine theta, divide through by the wavelength, that gives me an m value. And m is in numbers of cycles. Each cycle has 2 pi radians of phase. And so that's what this is keeping track of. At this point, the m value has only reached maybe an eighth would be the wave. So if this is 1/8 of a cycle, and then 1/4 would have this second phasor perpendicular, here would be 1/2. At 1/2, the two phasors would overlap and cancel out. And then when m equals 1, this would have gone all the way around one time and be back at the x-axis. So what this diagram is keeping track of is what would happen at any one of those possible orientations. And what we can show geometrically is that the A total, that is equivalent to doing vector addition. So it's the same rules that we might use if we were doing vector addition. The A total is going to be given by 2A cosine of the angle divided by 2. To find the intensity, intensities come from taking A total and modulus squaring them. Now again, the modulus here is saying if there's any complex numbers inside, I have to take that complex number and multiply it by what we call the complex conjugate. When those are multiplied together, I'll get a real value for the intensity. So, kind of interesting, nature uses imaginary and complex numbers, but when it comes right down to something that we can measure, those numbers go back to being real numbers. And then here is how the phase in radians is related to the m value. The m value is counting cycles, but for every cycle there's 2 pi radians. So to get that phase, I have to take the m and multiply by 2 pi. So that's what the intensities will look like. So again, I think you guys, if you look at the homework problems, if you look at the practice midterm problems, I think you're going to find everything is mostly working from the formulas that we've derived, not really deriving these formulas themselves. Okay, and so that pattern, the interference effect, the cosine squared value looks like this. Now remember, we said this is still a bit incomplete, but if we're just taking the interference effect into account for the 2 slits, 2 very, very narrow slits is what this pattern is assuming. And we're assuming that the distance to the screen is much larger than a wavelength, and we're assuming a circular screen, then ideally that's what the pattern will look like. And that's kind of like what that pattern is that we saw if we go way, way back. And I shouldn't do this. But this one, that's pretty, I guess it's not pretty uniform because we had the dropouts, but that's a different effect. We'll get to that in next chapter and see what's coming, why that's happening. Okay, so now what we're going to do is let's try another example here, I guess. This example is going to be looking at a radar antenna intensity. Now, I don't know if you guys have noticed, but if you're out along the coast, out along the Pacific Ocean here, driving along, every once in a while you run up to these Navy communication stations, and they have these big antennas that are headed up into the sky. You know, these really tall antennas, or sometimes an entire array of antennas. And what that is it's an interference effect that they're using. What they can do is they can control those antennas in a way where they can create particular directions that they want to send signals out to. So that allows them some kind of control over the direction using interference effects. So the idea in this example is, what would happen if we have 2 of these radio antennas, one located here and one here, and a lot of times these are just these really tall poles, separated by a distance d, and the antennas are radiating in phase. So if they're radiating in phase, what that's going to do is it's going to have an intensity peak right directly out ahead of those antennas, and actually behind the antennas too. So you're going to have peaks right ahead, and then at some angle you'll have an n equals 1, and at some angle you'll have an n equals 2, and so you're going to have varying peaks with these 2 sources. So let's try that. Here are these 2 radar antennas. It's the radio part of the spectrum now. Let's say that the wavelength is 100 centimeters. That's a frequency of 300 megahertz. What was the information they gave us? Did they give us the wavelengths? Oh, they said that d is equal to the wavelength. I'm not seeing the numbers. Am I missing this? Maybe I just put the numbers in. I just don't. Yeah. All right. Yeah. I don't see numbers. I must have just put those in to show what the effect might be. So let's go with that. Let's say, in any case, let's say that the wavelength is equal to d. So what's going to happen here is if the wavelength is equal to d, then the maximum value of m is going to be 1. So here we go. For d is equal to lambda, m will become d sine theta over lambda. The d and the lambda drop out. So that says m is just equal to the sine of theta. So when m is 0, theta is equal to 0. When m is 1/2, theta is the inverse sine of 1/2, is 30 degrees. And then m equals 1 will land at 90. If we convert that into a circular screen or a circular set of directions, it says we're going to have a peak in this transmission that goes right out in front, and then we'll actually have some zeros at 30 degrees. So there's a peak here, and then this gradually drops off and we hit zeros at 30 degrees, and then it picks up again and we have another peak going at 90. So peaks going here, peaks going here, and then zeros at the 30-degree angles is what will happen. Now what we can do, it says that currently what they're doing, I just don't remember where I wrote these down from, but anyway, this is probably just an example of frequencies and wavelengths that might be used for this communication. If we drive the two antennas so that the antennas themselves are a little out of phase, that would allow us to take the peaks and shift them to any angle we want. And if instead of just having two antennas, if we have a whole series of antennas, we can make that signal even more directional. We can control it so most of the intensity just goes off in a few directions. All right. So this interference, the interference effect is for real. This really does happen. And then in part C, what they're saying is repeat, here we go. Repeat this when d is equal to 1/2 lambda. So when d is equal to 1/2 lambda, then what we're going to have is this interference effect. It's going to be a cosine squared again, but this time when d is equal to 1/2 lambda, when these two antennas are just a half wavelength away, the m values at 90 degrees will be 1/2. So this would say that we're going to have a fairly, this is kind of spread over a lot of angles, but the peak would be right directly ahead, and then it would zero out at 90 degrees. So depending on the spacing of the antennas, depending on the frequency and the wavelength of the radio signal that we are using, the wavelength here is only 100 centimeters. So that's only a meter. Okay, I'm thinking the ones I'm thinking of along the coast are really obvious. They're really tall antennas, and so the wavelengths are probably quite a bit larger, and the spacing between them would be quite a bit larger also. But we could imagine putting different numbers in for that. All right, let's move on from the two-slit example, and let's take a look at another interference effect. This is something that I'm guessing you guys are familiar with. I'm guessing that you've probably seen this sort of stuff. This is an interference effect called interference due to thin layers of materials, or what's called thin films. Now, I think you guys have probably seen soap bubbles. If you look at soap bubbles really carefully, you see that there's a whole pattern of colors in there. Now as a kid, I remember sitting in the bathtub and looking at the bubbles and staring at them, and I kind of ran across this. I kind of discovered these colors in the soap bubbles And it was just amazing. I just sat there and I thought, look at all those colors in the soap bubbles. And then I also remember myself thinking, I am not going to mention this to anybody because they just aren't going to believe me. No one's going to believe me that there's a bunch of colors going on in these soap bubbles. But of course, there really are. Now, what is it that creates this effect when we have a thin layer of some sort of transparent material? So let's take a look at this and see where this interference effect is coming from, and how is it that this thin layer of material is actually able to generate this wide range of different colors. It doesn't seem like it's an intrinsic property of the material itself. It actually has something to do with the thin layering. So let's look at this. Let's say that we have, well, this is a bit of a different example, but here's water. Here's a very thin layer of oil. So that's the thin film. So there's a thin layer of oil, and then there's air. When we look at that oil layer, and you guys have seen this, right? In fact, you're probably seeing this now, kind of the first rainy seasons of the first rains of the rainy season. When you look in the gutters and on the streets, there's been a buildup of oil during the summer and spring, and now when the water starts running through there, you can see that that oil is maybe at the surface, and a thin layer of oil will definitely produce this interference effect. And where the interference is coming from is this. We have light that's illuminating the oil and the water, and the light has two possible paths that it can take. One would be a reflection off that top surface, and one would be a reflection off the lower boundary. So this gets us back to the idea of, well, if light can take two different paths to reach the same point, those two paths, when they come together, I have to consider an amplitude for each one of those paths, and then combine those, sum those together to get an overall amplitude and decide, are the two paths constructively interfering or destructively interfering, and am I going to have a large intensity for that particular light. Now, what that's going to come down to then is both, the light is traveling just, let's say there's one path coming in, and then the two paths split. So this path down to B and back, it's longer. That's extra path length. That certainly could introduce a phase shift. That's going to create a different sort of phase difference. And then when it comes back, it turns out that there's also the possibility of a phase shift when light reflects off a surface. So there's two effects we've got to keep track of. One of those effects is the extra distance the light travels in reaching point B. The light on path 2 goes from A down to B back to C. And then each of the reflections, the reflection at A, the reflection at B, there is a possibility of a phase shift there also. Let's go in and add all these effects together. But first of all, let's look at one more picture of this. Here's another example of this. And what you can show, this is an effect called Newton's rings, is that as you look at different locations between these two pieces of glass, what we have is a thin layer of air. So the thin layer, or the thin film, is air in this case. Now, again, I can have the light come down, and it can reflect from this lower surface on the upper curved piece of glass, or it can reflect off the top surface from the lower piece of glass. So it can reflect at point B or reflect at point C, and those two paths can recombine. And when I look at these two paths, there's going to be an phase difference, and the phase difference is going to depend on distances, right? Path number 2 went extra distance. It went from B down to D back up, and then also this possibility of a phase shift when the paths reflect. So we can take both of those into account. Now where this is really interesting is, look, with this thin layering effect here, we're actually able to, roughly, we're recreating the spectrum, right? We go from regions that are reflecting predominantly blue light, and then green, yellow, orange, red. So we can kind of see which parts of the spectrum are being most strongly reflected, is having the strongest interference effect. So now this is the effect where we said when things reflect. So if I have light coming in and it reflects and comes back out, if the index of refraction of the material that it reflects off of, if N2 is greater than N1, then this creates a half cycle shift. So there's a half cycle shift that takes place here. And I don't know if they've got this quite drawn correctly. I don't think they do. The difference between where this leaves off and where this picks up is going to be a half cycle. So I think it should actually pick up right there. So I'm not sure if that drawing is done right. Now this is the easier one. If light's coming through a material with index of refraction N1, and it bounces off another material where N2 is less than N1, then it doesn't happen. So wherever the wave was in terms of its phase, wherever the phase was, it's going to pick up right where it left off. And here it's going to introduce a half cycle. And that's what the words are saying the very same thing. Yeah, reflection off a material with a higher index of refraction creates a phase shift of 180 degrees, or a half cycle, or pi radians. Those are all ways of saying the same thing, right? And then reflections off something with a lower index, that effect doesn't occur. So here we go. Let's outline this. What's going on? So here is the thin layer, or the thin film. Thin layers, thin films provide two possible paths, and because there are two possible paths, we could have interference effects happening. So path number 1 compared with path number 2, let's count the cycles. So anywhere path 1 or path 2 has additional path length or a phase shift of some sorts, let's write that in. So as I look along path 1, well, path 1 takes this kind of shortest path. I'll say that's no additional path length. But path 2 goes all the way down and back. Now I'm going to say that the thickness of the film, the thickness of that thin layer, is B. And so the distance down and back is 2B. And if I want to count the number of cycles, that would be 2B divided by the wavelength. Now the wavelength inside a material with index of refraction N. So the N here refers to the index of refraction. The wavelength of the light is going to become wavelength divided by N. Whenever the light's passing through a material, the wavelength gets shortened, and it gets shortened by a factor of 1 over N. All right? I know that's a lot of rules to throw out there. And so the extra path distance divided by extra path length divided by the wavelength within the material, that will create some number of cycles. So path 2 gets that, path 1 does not. Now, there is also this half cycle phase shift when the light reflects. Now that could be yes or no, depending on the indexes of refraction. So the way we can break that down is this could be yes or no at the first surface, depending on what the indexes of refraction are on either side, and this could be yes or no. Now what can happen is, if it's yes, then we want to include a half cycle. If it's no, then we leave that out. That applies for each one of the surfaces. So if it's yes, yes, then the two halves cancel out. If it's no, no, the two zeros cancel out. If it's yes, no, or no, yes, then one of the halves remain. And so at the end of the day, what we're interested in is how many different cycles, how many additional cycles were there along path 1, how many additional cycles were there along path 2. And the overall phase difference will depend on the absolute value of M1 minus M2. If it's yes, yes, or no, no, then the total M value will be 2NB over lambda. If it's yes, no, or no, yes, then M will equal 2NB over lambda plus a half. We'll have one of the halves left over. All right, I know it's a lot of rules to keep track of. Let's try an example. So we're going to have a thin layer of air. Here we go. This is kind of an interesting setup. We have these very, very rigid flat pieces of glass. And we have something stuck inside here, a fine wire. So here is a wire. It's only 7.35 microns in thickness. And so across here, what we're seeing is this really nice interference effect. Now this would be kind of just a bunch of random differences in thickness of the air layer. But here, the two plates are really smooth. And so we're actually able to see a steady interference pattern where the thicknesses are varying. And then the light that we're shining on that is probably monochromatic, meaning that the light shining on that consists of pretty much just one wavelength, or a narrow range of wavelengths. Okay, so two flat glass pieces. The wavelength, so it's a 600 nanometer wavelength light, and we're looking from it directly above, and we're counting how many light and dark regions there are. Will the area next to the wire be bright or dark? Okay, so I guess we can count this. This would be where the two plates are right next to each other. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like we have about 10 cycles of increasing thickness. So that would be about 10 wavelengths thick. So we're guessing that wire is about 10 wavelengths. Let's check and see. Let's run the numbers and see what we've got here. So, the thickness was given. Never mind. The thickness, which I'm calling B right there, is given as 7,350 nanometers. Notice I already put that in nanometers. So you guys got to be a little nimble with the units conversions. Be ready for that. Be careful because, again, it's easy to be off by a factor of 1,000 or a factor of 1,000,000, or you don't want to be off by a factor of 1,000,000, right? So the nanometer, 7,350, the wavelength of the light coming in, they're telling us, is right at 600, and the index of refraction of the thin layer of air, we're just going to call that 1.00. So that is the thin layer. That is the N value that goes into here. Now, as far as reflections, we are going to have a mix. We're going to have yes and no. And I got those backwards. How did I do that? Okay, so it's actually, I have the yes and the no wrong, but I have the right number. It's not really yes, no. It's actually no, yes, because here the light is reflecting off a lower index, so it won't have a half cycle shift. Here it's reflecting off a higher index material. The glass is higher. That's the yes, that's the no. But yes, no works the same as no, yes, so we're still good to go. So the formula we want to work with does contain an extra 1/2 in it. And what I want to do is solve that for B. When I solve that for B, this is the formula that I get. Now, B thicknesses, they can only be positive, so the M values are going to begin with 1/2. So if I put in 1/2 for M, that's perfectly in terms of differences in terms of the cycles, the M values are going to give us, the half integers are going to give us destructive interference. So the dark bands that we see will happen at the 1/2, 3/2, 5/2, 7/2, 9/2, and those thicknesses are 0, 300, 600. So those are the thicknesses of the dark bands. So if we start over here at point A, and I have to say, I'm not sure, these shouldn't be round, they should be square, rectangular, because the bands are too short over here to see what's going on. But right at the contact point, where they're actually making contact, that should be destructive interference. And the reason for that is because, remember, we're getting reflections on each of these surfaces. That one does not have a half cycle, this one does. And so if we scale that right up to where they're directly in contact with each other, we're still going to treat this at it, even at that point right there, where there's no difference in thickness, or the thickness is 0, let's say, there's no difference in path length, there is still this reflection effect taking place. Okay, so anyway, these are the tables. The dark bands are going to be half integers, M. Those are the thicknesses at which the dark bands will occur for the 600 nanometer light. And the integer values, we've set it up so the integer values represent constructive interference. Those are the light bands, and those are alternating. So every 150 nanometers, we alternate between light and dark. And okay, this is not, so we got to go back and check the numbers they gave us. If B is truly 7,350 nanometers, then that would say M should reach 25. There should be 25 integer values that we cross, 25 half integers. There should be 25 light bands and dark bands, if those are the correct numbers. Do you guys see 25? I only count 10. So we've got something going on with the numbers they've given us, but that's okay. So the numbers they gave us were probably for a different setup where we had 25 bands instead of 10. So gradually increasing thickness of that layer as we move away from the direct contact point. And the M values are going from 1/2 to 1 to 1.5 to 2, 2.5, 3, 3.5, 4 as we make our way across. All right, here's another thin film example. And what it says we're trying to measure here is a soap bubble. So here it is. Here is the soap bubble example. The air on this side is an index of 1.00. The air on this side is 1.00. The soap bubble, they're telling us, has roughly the index of refraction value for water, a little higher. They're placing that at 1.35. Now, here are the two paths. The light's coming in. It bounces off surface number 1. It can also bounce off surface number 2. Now, this is going to be a case of yes, no. Because this is the higher index. When we bounce off the higher index, that's a yes. That's a half cycle. When we bounce off the lower index, that's a no. There's no extra half cycle. So, and the wavelength is 540. I think we got everything we need. The question here is, what is the smallest thickness that this soap bubble film could have? All right, how thin can that soap bubble become? Let's see, the wavelength is 540. The formula we want to use includes the 1/2, because in this example, it's, did I do this? Oh my gosh, I got this one backwards too. So I have to check and see if I understand the meaning of the words no and the meaning of the word yes. So this we would have the half cycle, here we would not. I think this was backwards day. Everything is backwards when I did these problems. Anyway, yeah, that's a yes and that's a no. Okay, so I'm solving for B. If I want to have constructive interference, is that what they ask about? Oh, the soap bubble appears green. So this is an interesting, this is good for us to talk about. So what it's saying is the soap bubble looks kind of greenish at this location, which means it's the green light that is constructively reflecting. Now remember, it's not on or off. It's not totally green versus totally not. It's gradual. It's going to be a mixture of colors. So it's not going to be just one wavelength of green that constructively reflects. There's going to be a number of close by wavelengths, a whole region of green that reflects really well. Okay. So here are the possible thicknesses. So I got the formula, I solved for B. Now when I look at this, depending on how I've set up the formula, this could be a plus sign or a minus sign, and it would actually indicate the same thing. Remember, we can always add a cycle, and it's physically the same thing is going on. So it just happens, the way that I counted the difference in cycles, I ended up with a minus sign here. What that tells me is M has to start out as being 1/2. 0 is not allowed for the formula, the way that I've set this up. And so I'm going to start with, well, M is equal to 1/2, but 1/2 would be a destructive effect. So for the constructive effects, I'm going to start with 1. So M is equal to 1, 2, or 3. The formula tells me the possible thicknesses here are 100, 300, 500 nanometers. 100 nanometers would be the thinnest soap bubble that would create this effect for a wavelength of 540. Now it could be 300 nanometers thick, and it would still constructively reflect the 540. It would still create that green effect. But it gets more diluted as the M value gets up. As the M values get larger, you get broader spreading of the wavelengths, so you get more spillover from other wavelengths. The most distinct effect will be for the lowest values of M. Now, for those of you who have played around with soap bubbles a lot, and I know you're out there, what you probably are familiar with is if you follow a soap bubble for a long period of time, eventually the colors get more and more towards the blue and the violet part of the spectrum, and then the colors go away. The soap bubble is still there, but the colors kind of disappear. Once the layer gets thin enough, it no longer effectively reflects any of the visible part of the spectrum. And you know that once the color goes away in your soap bubbles, what happens next? They pop, right? So what you're watching is the water is evaporating away from the soap bubble, layers getting thinner, the colors go away, and then at that point, you know, it's getting so thin that it's fragile, and then it pops. Okay, very good. I knew that you guys were out there watching these soap bubbles. So here's an example, though. Here's a good example to go in and ask ourselves, well, let's see, is it just the 540 nanometer wavelength that is undergoing constructive interference? So let's see what other wavelengths are out there. So what I did was this. I tried some different wavelengths. I said, let's run the same numbers. This is my intensity formula. And my intensity formula looks the very same as it did with the two-slit interference. Why does the intensity formula look the very same? Because it's two paths undergoing an interference effect. So in that sense, it's kind of the same thing going on. So what I need to do is just find out what the M value is for different wavelengths. So what I did was, well, it's not that formula there. If I come back to here, there we go. So if I come back to here, now that I know what the thickness is 100 nanometers, I can put the 100 nanometers in, and I can put in the 540, and I can put in the index, and sure enough I'll find that m is equal to 1. Okay, so when we're right at 540, the m value is 1, and the relative intensity is 1 from our formula. But what happens at 560 nanometers? That's not so far away from 540. Well, if I go to 560 nanometers and redo that calculation of m from the previous slide, it comes in at 0.982. Well, that's actually a pretty good sized m value. That's almost 1. When I calculate the cosine squared of m pi, I find that at 560 nanometers, I'm still getting a relative intensity of 0.997. All right, so it's saying that 560 nanometers works just about as well as 540 for reflection. And then if I move to the red end of the spectrum, at 700 nanometers, the m value for that is coming in at, and this is B is 100 nanometers, is coming in at 0.886, and the relative intensity there is 88. And for the blue at 400 nanometers, the m value is 1.175, and the relative intensity works out to be 0.727. So we're not really eliminating any of the visible part of the spectrum. So when I look, let's go back and look at one of these soap bubbles because they are so cool. There it is. So when I'm looking at the soap bubble and I'm seeing that region's kind of yellow, and that's kind of red, and that's kind of blue, it's actually a combination of the entire visible spectrum. But as we look at different locations and different thicknesses, some parts of the spectrum will be favored compared with others. But it's not like one is there 100% and one has been completely removed. That's not the case. Okay, so here are some suggestions for solving problems with these thin layers, these thin film interference. And I think we've got one last example here. I think this is going to wrap up the chapter. And what this is asking about is non-reflective coatings. So, you know, when you go to the optometrist, I have to tell this story, when you go to the optometrist, they always say, and would you like a non-reflective coating on those glasses? And I'm never sure how to reply. I'm not sure how effective the non-reflective coating is. And so on these reading glasses, I thought, well, I'll just try it without the reflective coating. And what I'm finding is, I think they're fairly reflective. I think I needed the non-reflective coating. Anyway, here's kind of the physics behind how that would work. So I know I teach this stuff. I should get the reflective coating, right? That would be the obvious thing to do. What they're saying is we can put on a thin layer onto these glasses. We can put on a thin layer of magnesium fluoride. And the magnesium fluoride has an index of refraction, 1.38, and it's designed to eliminate reflected light at wavelengths in and around 550 nanometers, which is right at the center of the visible spectrum. The glass behind the magnesium fluoride has an index of 150, so this is the higher index. Now we need to know that because we have to determine our yeses and nos, and I hope I get it right this time, or else I just keep getting it wrong every time, and so it works out, my answers work out the same. This is saying yes, and this is going to be yes, because the indexes just keep getting larger. So this should be yes, yes. Let's see if that works. Okay, see if that's how I set this up. Yes, yes, I think I got it. Look, yes, yes, this time I think I might have done it right. So yes, I'm going to have a half cycle. Yes, I'm going to have a half cycle. So in my formula then, the 1/2 is not there. It's just m is equal to 2nb over lambda. This is what I should have realized at the optometrist when I was getting the or the optician's office. So let's see. So the coating is going to be 100 nanometers thick, and now I'm trying to remember what numbers they actually did give us. What is the thickness? Yeah, we're supposed to be solving for that. So, did I solve for it? All right. It should be coming from here. So what we're looking for is destructive. Oh, I see. Got it. So here's where I actually solved it. That's based on what we solved for here. So the thicknesses that will work are those where m is a half integer, either 1/2 or 3/2 or 5/2. Those should work. I'm going to go with the m equals 1/2, which is 100 nanometers. So 100 nanometers works, basically 300 nanometers works, 500 nanometers work. Those are some possible thicknesses. If I want to concentrate on just the narrowest range of wavelengths, I'll go with the 100 nanometers. Okay, let's see what we can do with the different wavelengths. See how well this non-reflective coating is going to work across the visible spectrum. So I looked at red, green, and blue, and the wavelengths I picked, I should have picked 700 and 400, but I went with 650, 550, 450 to represent those three regions. And when I solved for M, for the 550, I came right in on M is equal to 1/2. Now that's not a coincidence. That was the condition that we set in order to get this thing to be non-reflective for the 550 nanometer wavelength. So this was intentional. Now by picking this M value for green, when I went to the red, well, the M value here is 0.425. That's pretty close to 1/2. When I did the relative intensity using that formula right there, and by the way, I don't know if I've mentioned this specifically, but this formula uses radians. These are phases that are going into these formulas, and phases traditionally are measured in radians. So I've got to make sure that my calculator is set to radians. I can take m times pi, and then make sure the calculator is in radians, and then do the cosine and square it. So when I did that, and I got the relative intensity of the red light, I'm finding that the reflected intensity is only at 5.5% of what it would be otherwise. The green light is completely removed, and the blue light, well, at the 450 nanometers, the M value is 0.613, and so the relative intensity here worked out to be 0.121. Okay. Anyway, that's what it's showing, is that with this thin layer of magnesium fluoride, we are able to remove reflection. We're able to highly suppress reflection all across the spectrum. I'm still wondering why I didn't get the anti-reflective coating. It seemed like an obvious enough thing to do, given I teach physics. Anyway, I may have to go back and get some, I'm going to go back and get some new lenses made up. Maybe I'm time for a new prescription. And then get the non-reflective coating this time. And then I can do a side-by-side comparison. Now that sounds like somebody who teaches physics, right? All right. Now there's a couple of later sections in here that I guess we could go through quickly. Oh, this is the last slide. Okay, so what we can do is, this is a measuring device. It's called a Michelson interferometer. And what we can do is we can take a source of light, we can send it through what's called a beam splitter. So it's not complicated. We can just take a plate with some glass. You guys will see this when we do the speed of light lab. You'll get to see what this looks like. So I just take a beam splitter, a piece of glass, and some of the light reflects off the front surface and then comes back. And some of the light goes through and comes back and then reflects. Now I'm also getting reflections in different directions, but the two paths we're interested in are path number 1 that does this, and then path number 2 that does this. And when those two paths come together, they're going to generate an interference pattern. So we can set up a screen and take a look at the interference pattern that has been produced. Now what we can do is now it says we're going to fix this mirror and only move this one, so let's do that. I'm going to fix this mirror, and then what I'm going to do is move this mirror back and forth ever so slightly. Now if that mirror gets moved by even one wavelength of light, so the light that I'm using might be 400 or 500 nanometers, if this moves even by 100 nanometers or so, that's going to be enough that the interference pattern that shows up will show a definite change. I can watch, with this, I can watch the pattern of circular, bright and dark circles using this Michelson interferometer. So these are used to do very sensitive distance measurements, and specifically measurements to see if anything is happening with this mirror. Is there any kind of a difference in distance that's going on with these interferometers? So these are really interesting devices to make those sensitive distance checks. All right, I think that's it. So we've successfully made it through our first chapter of quantum light, and we've looked at these different paths. We've looked at interference effects. We have one more chapter where we're going to look at, we're just going to continue to look at the quantum effects of light. So whatever questions you guys have, definitely stop by. Office hours, and we will take a look at whatever questions you've got.